All right, what we're going to do now is take a little bit about what we learned in the last video where we talked about how transistors represent 1 or 0. Each transistor represents 1 or 0. And by putting them all together, we can represent a binary number. And what we looked at was, and we're starting this discussion with something called unsigned binary. Unsigned binary basically means we are using transistors to represent values from 0 up to some value. And that's based on the number of transistors that we've got assigned to represent this particular value. And there's a pretty easy way to convert it. We talked a little bit before about how if you've got, for example, 10 digits, the highest value we can represent with this 10 bits is, well, this was the 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 5, 6, 7, 8, 9. This is the 2 to the 9th position, 512. And remember, if we added up all those powers of 2, we came up with 1023. The next digit, if I had an 11th finger over here, would have been the 2 to the 10th position, or 1024. So, for n bits, what we can represent is 2 to the n minus 1. This is if we have an n-bit binary value. And so I can tell you 8 bits, that's typically what we're going to represent things in this class. That would be 2 to the 8th minus 1. 2 to the 8th is 256, minus 1, 255. So most values are going to be represented with, anything that is 8 bits can represent up to 255. Now, I'm going to make this little rectangle. And what we've got is each one of these boxes contains a 1 or a 0 based on what the transistor contains, right? And if we had had this 9th bit, this would have been the 2 to the 8th position, or 256. So this position right here is the 2 to the 0, or 1. Then we have 2 to the 1, 2, 2 to the 2, 4, 2 to the 3, 8, 2 to the 4, 16th, 2 to the 5, 32, 2 to the 6th, which is 64, and 2 to the 7th, which is 128. So this, we can represent values up to 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, or 255. All right. In fact, let's go ahead and put a pattern of 1s and 0s in here. Now, I don't know. How about 0, 1, 1, 0, 1, 0, 0, 1. All right. Now, I've heard this described in a number of places, but Bill Gates in The Road Ahead talks about how he describes binary to somebody who's not familiar with computers. He says, imagine that you've got 8 light bulbs here. One is 128 watts, then we have a 64 watt, 32 watt, 16 watt, 8 watt, 4 watt, 2 watt, 1 watt. What is the total wattage when we turn on a specific pattern of light bulbs here? Well, in this case, what we've got is 64 watt is on, 32 watt is on, 8 watt is on, 1 watt is on. So we've got a total that we can represent with this guy of 128 plus 64 plus 8 plus 1. Add all those, oops, sorry, not 128. Getting ahead of myself, wasn't I? All right, so, sorry, we have 32 plus 64 plus 8 plus 1. All right. 32 plus 64, 96, plus 8, 104, plus 1, 105. Now, we count in base 10. And so whenever I represent a base 10 number up here, I'm going to put this little subscript 10 there in order to indicate that we are talking base 10. For example, if I put the value 100 up here on the board, 100, well, is that a base 10 or is that a binary value? I need to put that subscript up there so that you understand whether we're talking about base 10 or base 2 or base 16 or base 8 or any of the other bases that were out there. So this number right here, this 011010001 base 2 is equal to 105 base 10. All right. Now, it's pretty easy to go from the binary to the decimal, right? What about going the other way? What if I have something other than a squeaky pen? What if I've got 8 transistors that I want to represent a value in? Now remember, these transistor positions are 1, 2, 4, 8, 16, 32, 64, 128. All right. Now, what if I want to represent the number 143 base 10? The very first thing to do is to double check and make sure that the bits that we're allotted are enough to represent that number. Are they? Well, remember with 8 bits, this position right here was the 256 position. All right. Is this number less than 256? It is. So that means that we can represent 143 in those 8 bits. Now, how do we do it? Well, the way we do it is, and there are a couple of tricks, but what we're going to look at right now with this particular video is you take out the largest power of 2 you can from this guy and have it still remain positive, right? So what is the largest power of 2 that is less than or equal to 143? Well, it turns out it's 128. So we pull out 128. Pulling out 128, we get 15. So we turn on the 128 light bulb, and we've got 15 watts left to figure out how to represent. 64, too big. There's a 0. 32, still too big. 0. 16, close, still bigger. So we put a 0 there. 8 is the next highest power of 2 we can pull out of 15. So we pull out the 8, we're left with 7. Now that we've pulled out the 8, oh, and turned on the light bulb, of course, what's the next largest power of 2 we can pull out? Turns out it's 4. So we pull out the 4, we get 3. Turn on the 4 light bulb. 2 is the next largest power of 2 we can pull out. We pull out a 2, we're left with 1. Turn on the 1 light bulb, you pull out the 1, and now we've got 0. Now, the key here is that we have to end up with 0. No digits left, no value, no magnitude left. If you get to this point, if you've gone through all of your bits, and you don't end up with 0, one of 2 things has happened. Either the first thing is you didn't do the check to make sure that the value we are trying to convert is less than the value, less than or equal to the value that we can represent with a given number of bits. And remember, we can use this expression up here, the 2 to the n minus 1, in order to determine that. The second thing is that if we don't end up with 0 down here, is maybe there was a mathematical error. Maybe we did the subtraction wrong. If we did the subtraction wrong, that's a pretty easy fix, right? Just redo the subtraction. So what we've got is 143 base 10 is equal to that pattern of 1s and 0s. 1, 0, 0, 0, 1, 1, 1, 1, base 2. Now, the key is this is just one way of representing a decimal number in binary. This is, once again, referred to as unsigned binary. We will talk about signs later on, but right now, positive, non-negative values are what we're looking at representing here.